Hello everyone, I'm Qing from Tsinghua University. Thank you for joining the presentation. My talk today is about Cognitive SSD, and it is a collaboration work from University of Chinese Academy of Science and Tsinghua University. As you can see, I'm not in the author list, but I will try my best to share the work with you. Cognitive SSD is designed for unstructured data retrieval. Data retrieval system aims to search similar data from the database. However, traditional systems suffer from the issues of inaccuracy and power inefficiency. Therefore, we propose the Cognitive SSD, which integrates deep learning and graph search to provide better retrieval performance, and leverage near data processing technique to address power inefficiency issue. In summary, Cognitive SSD provides an energy efficient and in-storage unstructured data retrieval solution. This talk contains 5 parts. First, I will introduce the background and the motivation. Our system is designed for unstructured data, which cannot be directly recognized by the computer. More importantly, Intel and IBM reports indicate the unstructured data has grown explosively and occupies to 80% of storage capacity in data centers. This data will generate intensive retrieval requests. Therefore, it is critical to support fast and energy-efficient data retrieval in the cloud infrastructure to reduce the total cost of data centers. However, traditional data retrieval systems suffer from the issues of inaccuracy, power inefficiency, and high cost. From the software perspective, the current I/O stack of Linux system that is designed for hard disk driver significantly burdens the retrieval system, especially after using the high-end storage. For example, the latency of I/O stack equals NAND flash-based SSD and is 5 times Optane SSD. Meanwhile, from the hardware perspective, the data at the low-level storage must travel across a slow I/O interface, main memory, and caches before reaching the computer units. This will incur energy and latency overhead. The content-based unstructured data retrieval system contains 2 stages, feature representation and database indexing. However, traditional feature representation and database indexing methods cannot provide accurate retrieval performance. Therefore, we leverage the deep learning, the deep hashing, and graph search to provide better feature representation and perform fast and high accuracy retrieval. To address the above software and hardware issues, first we combine the deep hashing and the graph search to perform better accuracy retrieval and integrate them into the DLG-X Accelerator to simplify the software stack. Meanwhile, for fully using the internal bandwidth of SSD and address the long data movement path problem, we leverage the near data processing techniques to put the DLG-X into the SSD to construct the Cognitive SSD. In this manner, the DLG-X could obtain data directly from flash, bypass conventional memory hierarchy. Meanwhile, we also provide user-visible software abstraction to improve the scalability of the Cognitive SSD system to support different applications. Next, I will explain how to deploy Cognitive SSD system. The Cognitive SSD system contains 2 parts. The DLG library running on the user level space is responsible for controlling and communicating to the Cognitive SSD. Based on the NVMe protocol, we provide the configuration command DLG config to configure the DLG-X accelerator and the task command such as DLG hashing to generate the hash code of input data. DL command such as SSD read could access the physical address of the Cognitive SSD. The firmware and the hardware of Cognitive SSD receives and processes these requests from DLG library, where the Cognitive SSD communicates to the host server by the PCIe interface. As mentioned above, Cognitive SSD combines the deep learning and the graph search technique. Therefore, 2 issues need to be addressed in DLG library. First, how to update the deep learning model and the graph parameter. To address this problem, we provide a DLG-X compiler that supports a deep learning framework to transfer the deep learning model into the instructions of DLG-X and generate graph parameters. After that, users can invoke command to write these instructions and the parameters into the Cognitive SSD. The second challenge is how to dispatch requests. To address this problem, we construct the task plane to send a request. Meanwhile, the task plane also provides the user-defined API interface to enable users to deploy other applications without much modification. This API could be configured to read the results of any module of the Cognitive SSD system according to the instruction and the user configuration. Meanwhile, we also provide the data plane to enable users to access the physical address of the Cognitive SSD. The firmware of Cognitive SSD manages the request from the DLG library. First, the DLG configurator receives command and writes instructions and parameters into the instruction and the parameter area of the NAND flash. Second, the DLG-X task scheduler push requests into the queue and issues command to the accelerator. Third, the I/O task scheduler is responsible for issuing I/O requests to the DLG accelerator or the NAND flash controller. After introducing the Cognitive SSD system, I will introduce the details of the DLG-X accelerator. First, traditional deep learning accelerator obtains metadata from the DRAM. Although SSDs often have a compact DRAM to cache data or metadata, the internal DRAM capacity can hardly satisfy the numerous neural network parameters. Therefore, we expose the NAND flash controller to the DLG-X accelerator, which enables the DLG-X to read the related data from NAND flash bypass the internal DRAM. Meanwhile, we also prove that the bandwidth of flash exceeds the demand of convolution layer. For fully connected layer, we only use the one column of P array to balance the bandwidth of the fully connected layer and the NAND flash. Due to the NAND flash controller could read data in parallel, the data layout on NAND flash will impact the performance of data transmission, especially for the fully connected layer. Therefore, to address this problem, first, we split the deep learning parameters according to the number of the channels used by the DLG-X to maximize the parallelism of NAND flash. Second, we leverage the advanced command provided by the NAND flash manufacturer to improve the throughput of NAND flash. After introducing the deep learning part of the DLG-X, I will explain how to achieve a graph search on DLG-X. First, the graph search stage is similar to the deep learning algorithm, and it contains an online stage and offline stage. In the offline stage, the DLG-X library uses DLG-X to generate a hash code to construct a directed KN graph. In the KN graph, vertex represents a data entry. After that, in the online stage, the DLG-X generates the feature of user's data and map it to the KN graph. Then, based on the concept that the neighbor of a neighbor is also likely to be a neighbor, the DLG-X checks the vertex of KN graph to find the true neighbors of the user data. However, NAND flash read operations are performed at a page granularity, so that every time the DLG-X accesses the neighbors of one vertex, it must read a page from flash. This can cause low bandwidth utilization if we place vertex and their neighbors in flash memory sequentially. To address this problem, we can infer that the neighbors of the accessed vertex will be used soon due to the spatial locality. Therefore, the neighbors of vertex and neighbor's neighbor are aligned and stored from the beginning of a page. As a result, such a layout with redundancy can reduce the flash access compared to the non-optimized graph layout. We use the image retrieval system as a showcase to explain how to deploy the Cognitive SSD system. First, we inject image data. Second, deploy deep learning model and the graph. Third, cognitive system could receive requests from the internet. For the first step, the users invoke the API of a data plane to inject image data into the NAND flash. Second, user leverage the deep learning framework to training a model for image database. After that, user uses DLG compiler to generate instructions and graph parameters and read them into the NAND flash. Finally, when cognitive SSD system receives a request, the task plane will send this request to the task scheduler. When DLG-X receives command, the deep learning unit generates the hash code of user data, and the graph search unit searches similar data, and then transfers the ID-directed results stored in NAND flash to oh, sorry. The task plane will send this request into the task scheduler. When DLG-X receives command, the deep learning unit generates the hash code of user data, and the graph search unit searches similar data and then transfers the ID-directed results stored in NAND flash to the host server by using the PCI interface. Finally, I will introduce the evaluation part. First, we build the cognitive SSD based on the OpenSSD platform, which includes a Zinc FPGA chip, 1 GB DRAM, 8 channels NAND flash, Ethernet, and the PCI interface. The DLG-X Accelerator and the NAND flash controller are implemented on the FPGA chip, and the firmware running on the ARM processor or FPGA chip. Meanwhile, we also built 4 baselines to show the performance of the cognitive SSD. And we select the content-based image retrieval system as workload. We leverage 4 different scale datasets to evaluate the performance of data hashing and the graph search algorithm. The results indicate that our DLG solution performs better retrieval accuracy regardless of the choice of t-value when compared to the conventional hash solutions. It also shows the robustness of the DLG solution when deployed on a real-world system. Meanwhile, we compare the latency and the power of the deep hashing unit and the graph search unit on DLG-X Accelerator to the solutions based on the CPU and the GPU. The results indicate that the deep hashing unit of the DLG-X outperforms CPU solutions. But due to the FPGA resource and the frequency limitation, the latency of the DLG-X is higher than GPU, while the GPU consumes more power than DLG-X. Meanwhile, we also witnessed that the graph search unit of DLG-X outperforms CPU solutions. We built a web-accessible CBR system to evaluate the latency of the system and utilize the matrix of kbps per watt to evaluate the power efficiency of the system. The results indicate that the cognitive SSD could reduce latency by 69.9% on average compared to the CPU solutions and more power efficient than the GPU-based system by 2.4 times. The cognitive SSD on conventional cluster system only occupies 14.08% power consumption of the system. Meanwhile, considering the cognitive SSD contains the ARM processor that could run the Linux system and has lower power consumption compared to the Intel CPU, thereby we propose a host-free cluster system where the cognitive SSD as a server can respond to users' requests independently. The results indicate that when system concurrency is low, the host-free cluster system delivers better power efficiency. The reason is that using high-performance machines to handle infrequent requests results in low energy efficiency. The host-free cluster system will be more power efficient if the Cortex-A9 processor is replaced by the latest Cortex-A series processor. In summary, we built a cognitive SSD that provides a more power-efficient solution for unstructured data retrieval. First, the internal DLG-X Accelerator integrates the deep learning and the graph search to provide better retrieval performance. Second, DLG-X directly accesses the data from NAND flash bypass memory hierarchy. Finally, our FPGA-based prototype indicates that Cognitive SSD outperforms other solutions on power efficiency. Thanks again for listening, and since I'm not familiar with the details of the work, if you have any questions, you can contact the author directly. Thank you.